SwayamPrabha. Digital India. Educated India.
Welcome back. This lecture 10 would be on land use transportation model components and future challenges. The different concepts covered in this lecture are components of a land use transportation model, software architecture for urban simulation systems, land use components in existing comprehensive mobility plans, and future challenges. So, starting with the components of land use transportation model, the first component is the accessibility model. So, this model determines accessibility values for users of each traffic analysis zone for access to different land use or activity. Now, this model is not directly affecting any change in the land use or the transportation process, but this is an intermediate model, values of which could be used in other models to determine criteria, determine location choice or determine your decision for a particular family to move, or for other or even for transportation part as well. Now, what is in this particular model is basically connected with the travel demand model, and when the travel time estimation from that travel demand model changes, automatically accessibility of a particular zone also changes. For example, because of congestion along a particular route, the travel time increases. So the route is connecting between zone A and zone B. So obviously zone A's accessibility reduces because the travel time increases. So and similarly, if the trip is originating from B and going to A, then zone B's the accessibility will also decrease. So this model is basically connected to the travel demand model, and travel time and multimodal travel utility. We have already explained the term utility. This means how much suitable or attractive is the different available choice basket of different modes in a particular area. So what happens, sometimes a travel demand model can also tell us availability of different modes in an area or viability of different modes, and that actually leads to utility of the transportation system in that particular area. So both these things changes when there is a change in the infrastructure or change in the and due to congestion and so on. So this comes as a feedback to the accessibility model, where the accessibility value also changes. Now, accessibility could be of two kinds. One is regional accessibility, that is in between two TSZ zones, we can say the accessibility value is estimated, and the other is local accessibility, which is within a zone. So local accessibility refers to basically how accessible the zone is, probably by foot. That means how easy it is to walk around inside the zone, or it could be local travel using maybe e-rickshaws and all. That also could be, if the zone is large, then we can have intra-zone travel using e-rickshaws. So this is the local accessibility part, whereas that is more related with infrastructure and all. Whereas regional accessibility could be infrastructure. For example, location of a bus stop. If there are many bus stops, the accessibility of that particular zone is high. But similarly, regional accessibility also talks about amount of opportunities that are available for trips for that particular zone, or for the people to do a particular activity. What are the different opportunities that are available? For example, how many movie theaters are there nearby to this particular zone? So that will increase the accessibility. Maybe for recreational trips, it will increase accessibility for this particular zone. So that is what the accessibility model is all about. So after the accessibility model, we have the economic transition models, and this model actually predicts the job creation and loss in a particular urban area. And what it means is during the planning period, or during the time when the model is being estimated, and there are certain jobs which are added and there are certain jobs which actually moves away from that particular urban area. So that is what this model estimates, and the control totals per sector as per economic forecast also needs to be aligned. That means if we have economic forecast, yearly economic forecast for jobs for each different sector, so once the job creation and loss, this part is modeled for different zones in an urban area, the total of all these jobs created and lost should match with the total of the economic forecast that was there. So that is what control totals talks about. So it's a sort of check to see that the forecast and the actual model matches, both matches. The prediction by both matches. So then comes the demographic transition models. So this model keeps track of births and deaths in households, and again in this particular model we also have got control totals as per population forecast, and here both we can check the household size, age or income groups. Probably we have forecast for this particular variables, and we can see that once the total amount of births and deaths are computed for different zones and we add them up, it matches with the control totals of the overall area or with the forecast for this particular area, and we can also match that for each of these birth and deaths. When we add them up, it matches with the forecasted household size or age and income group and so on. So to do this, we require also population or household synthesis and deletion. What means is, if we are doing a survey in a particular urban area, we cannot survey the entire population. We will only survey a handful of people, and they will represent the entire heterogeneous population that is there, and we can create a synthetic population using these characteristics of the population and their proportion of different socioeconomic groups in that population to create a synthetic population, so that we can apply models, disaggregate models, which actually changes with each person, will have different choices. So that's why we require to expand the sample into a synthetic population. So when we do that, then again we need to make sure that when we have our synthetic population, the total average or total number of different characteristics like household size, like how many families are there of different household size, or what is population wise, what is the age groups that are there, these totals match with the forecasted population totals for this particular area. So this is what is done in the demographic transition models. We will explain these models in detail later on in other lectures. So then comes the household and employment mobility models. These two models, basically these are two separate models. We have the household mobility model and then the employment mobility model. The household mobility model predicts the probability that a household will change location. That means it doesn't predict where it will locate, it will just predict will the household change location. Usually that happens when a household maybe there is a birth in the household and there is not enough space in the existing place where this household stay, so they need to search for a new residence. So that is why household may want to change location, or somebody gets a job in the household, then also the household may wish to change location. So this is what a household mobility model is. And similar to households, we can also predict the change of a job location. That means certain companies in an urban area can shift their location because the existing location probably is not adequate, or maybe the company wants to grow, so it wants to move into some other building and so on. So in a different location, of course. So this probability of a job to also change location, this also needs to be modeled. So when this happens, what happens is the existing space where this company or the household is occupying, that becomes available in the market for a next family or a next job to occupy, and this group of people are waiting to be allocated to a new area. So this happens in sequence. So in the next part, when in the next model, in the household location choice model, this model determines the allocation of a household without location to a new location. So you see the number of people who was without location, a number of households which were without location, number of households which were without location, this households will be allocated a new location, and this model predicts this particular allocation process. So usually we use a multinomial logic model as shown here, and it is used to determine suitability of a location for a particular household. That means if we have different kinds of households, they will have different preferences for different locations, and that is again determined through a utility equation. Whichever location gives them the highest utility, a household will move into that particular location. So that is a multinomial logic model, and because there are many choices from which a household can choose a location, that's why we use a multinomial logic model, which actually takes care of many choices. And finally, household is assigned to the most suitable location. So once we know the probability of a household to shift to a particular location, the one with the highest probability is the one where the household will shift. So which are the variables considered for this? For this kind of models, we usually require different kinds of variables. Some of the variables are more focused, are related to the housing type or the density or the age of the particular building in which the person is thinking of moving, or which is a choice for a particular household to move, and it could be either plot wise or grid wise, or it could be TZ wise. That means depending on the scale, we have to generalize. That means if we are looking at a scale where we are looking at TZs, so TZ level analysis, in that case we have to say average density for the TZ or average age of housing in the TZ, if I want to keep housing as a age of housing as a determining factor, or average price of housing in that particular TZ. If it is in form of a grid, which is of a smaller scale compared to a TZ, then it is a bit more accurate. And then if it is plot wise, then it is exact. That means for each plot we can have a price, and the housing can consider this price when considering to move in. So if it is plot wise, we know exactly what the density is or what is the age of that particular building in that particular plot. But if it is grid wise, then we have to take an average for that particular grid, and if it TZ, it is again average, but of course the size is more, and so the accuracy reduces. And then we can look into the land use mix, density, average property values of TZ. So this is more about the total characteristics of the surrounding neighborhood or the surrounding TZ. It could be also a zone surrounding that particular building. So this, if this is done at the TZ level, in most cases the first two become same, because we cannot have individual plot wise price density variation in a TZ. So this becomes more or less like a average property value in case of if we take TZ as the smallest zone that we use in our model. So as you can understand, household location choice models works best when we go for a smaller classification or a smaller zones. For example, we go grid wise, then the model's applicability increases. Local accessibility to retail. So this is another characteristic. So this is where the accessibility model contributes by, we can use the accessibility values calculated through the accessibility model in this one, and it can determine what is the accessibility to retail, and similarly regional accessibility to jobs also could be estimated from the accessibility model. So accessibility, which is basically different parts of different attributes of transportation, then the land use proper characteristics and the plot or the housing characteristics all play a role in a household's location to shift to a particular area. Similar to household location choice, we also have got employment location choice model, and this could be done for home-based jobs and also for non-home based jobs. So for non-home based jobs, job location is determined out of empty office space options available for non-home based jobs. So what it means is, for all new offices, new buildings, which is commercial buildings which have come up, so these are the empty offices for where a person can move, or offices vacated by other companies who wants to shift their location. These are also available spaces for which a company can move. So this job location or employment location actually looks into this, and then job location and then home-based jobs could be allocated randomly considering household characteristics constraint. So whereas Non-home based jobs are in commercial areas, whereas in commercial land use we have to shift them, whereas home based jobs are basically jobs which could be carried on in home, and that means that certain households are more susceptible to have a home based job in them. For example, a household having only a single person and he is already employed in a non-home based job probably doesn't have a home based job. But a household which has got two persons without any job, and probably one of the persons is among the houses, or both the persons is engaged in a home based job. So that's why it could be, so we can randomly consider existing housing where this home based jobs could be allocated, but at the same time we need to take into consideration the different household characteristics which could act as constraints in the model to determine where these home based jobs would be allocated. And then variables considered, again, because a company is company is trying to locate itself in an empty area or an empty building, where a commercial building. So there also it will look into certain attributes of that particular plot or that particular area, which it will be considered while thinking that okay, if this area is suitable or not, and that could be formed again in form of a utility for that particular area, or it could be estimated as utility for that area. So price, type, density, age of office space, again the same similar to housing, it could be plot wise, grid wise or TZ wise. These are the parameters for that particular plot or that particular grid, and then it could be average land values, land use mix, density, sector wise jobs available at the TZ level. So we can also, if we are looking at TZ level, then we look at average land price for that particular TZ, or the land use mix and density for the TZ, and the different types of jobs for different sectors available in that particular TZ, which can also play a role in my location choice. But location choice is actually the choice of the plot. So the more number of jobs are there, or a type of job is there, there is chance according to the capacity of that particular TZ, how many jobs it can take in, that also can be considered while allocating a particular job in a particular TZ. And similarly, we have a regional accessibility to population. This parameter could also be considered, which is again the transportation component in this particular model, which shows that okay, with improvement in transportation infrastructure or accessibility, then there is more chance for a company to move into a particular location. So the next model is the real estate development model. So this model actually predicts where new development or redevelopment is going to happen. That means not all, certain amount of redevelopment happens all over the city, but new development occurs only in certain areas which are growing areas, or which are the areas which have been added to the urban area recently, or areas where there has been a satellite township has come up in along with the existing town. So these are the new development that had areas, and this new development could include any kind of building. We can have many categories of building. We can look like we can define them as commercial, retail, housing. Then we can have subtypes. Housing could be of high-end residential, or for residences for middle income group, or it could be plotted housing, and so on. And similarly, retail could be of different kind. Commercial buildings could be of different kind as well. And in this particular model, construction decision of real estate developers is determined in terms of type and location. So both the type and location of that particular construction is actually determined, and here again we use a multinomial logic model which is used to predict probabilities. And again here the variables considered are the ones which influences a developer to choose a particular location to develop. For example, land price, policy constraints, land use and building use, and then again plot wise, grid wise, TZ wise, this could be the variables which influences a choice of a developer to build in a particular area, or it could be proximity to transportation infrastructure and other TZ characteristics. Our developer will always want to build in an area where there is adequate transportation, and because if he is building commercial, then it should be accessible from different parts of the city, and so on. So depending on the commercial or retail, housing or whatever kind of new development, the kind of proximity infrastructure that is more favorable also could be considered, different kinds of infrastructure could be stressed upon as well. So similarly, regional accessibility of population is also estimated, which shows that how accessible is that area from different surrounding regions. So this is this model is very closely related with the land price model. So this is the final model component where this land price model is used to predict the land price for a particular area. Now, land price model again, the land price of a particular area varies as per the infrastructure of that area, as per accessibility of that area, and it could be based on many other factors. So when land price changes, automatically this again directly doesn't changes the land use or choice or the transportation choice of people, but actually they actually influence the choice of a particular business to move somewhere or a particular person to choose a housing somewhere. So this is how the land price model influences the overall land use transportation interaction process. So then comes the software architecture for urban simulation systems. Now I use the term urban simulation systems because, as you can understand, there are several model components like real estate development model, household and development mobility models, accessibility models, economic and demographic transition models, household and employment location models, so land price models. So there are several models which are running together, and each input from one is going as output from one is going as input to another model, and so on. And so all the different components has to be tied up, and that is the job of the software, and that is what the software architecture actually decides how these things would be tied up and how the simulation will run. That means which one model will be run at what sequence and so on. So like in any programming, we have a main program from where we can call different functions or where we can initiate classes. So we have the model coordinator, and this model coordinator is the one which decides the overall flow and sequence of the program and how one iteration will happen, and then how the data from one iteration gets stored, and then again we take those data and take it as input for the next iteration and so on. So this sequence, how the entire modeling will run, is determined by the model coordinator. And as you can see, this software architecture is from the urban sim model which we have discussed earlier. So you remember this, in urban sim we have two external model. One is the travel demand model and the other is the macroeconomic model. So macroeconomic model along with the control totals when we are doing population synthesis, job synthesis and so on. So this part is particularly run at the beginning, and once this part is run, then we can also run the other models after that, because initially we require estimates for population, jobs and so on, and then we can also go for certain user specified events and scenario assumptions where we can envisage certain scenarios like at a certain area, or we can say that certain infrastructure has come up, or in certain events or certain kinds of we can decide that okay, certain area will have a higher density. All these inputs could be given before a model is run, and once it is given, we run the component models in sequence one after another, considering the relationship between this particular model. For example, the land price model computes the land price, the accessibility model computes the accessibility for a particular area. Then only we can determine the household and employment mobility models, and then parallelly we can run the real estate development model. But as soon as the real estate development model will run, then we get inputs that like certain new areas are selected for development. We keep that in the data store. We save this data because immediately these buildings are not available. These buildings would be available 3 years down the line. So we save that data, and after the model runs for 3 years, after three yearly simulations, then automatically this building is made available. It comes back and it becomes available in the market. It is again estimated along with it could be estimated along with the control totals over here, where we decide on the number of jobs and so on. and these are the models which are this data is saved and pulled out and also read back and forth, and it happens continuously, and whatever results come out, we can export the data, and it generates ASCII output files which could be used for again visualizing. Using a GIS platform, we can visualize the location choices of people and so on. So this is to give a nice face to the entire output of this particular model system. But as you can understand, this model coordinating the model is very important, and this sequence of which will run, how the things are related, this has to be followed very, very carefully. And if we want to develop something similar in our context, there also we may find that not all the we may be able to model all the things. We may be only able to model certain things. The others would be like exogenous input into the model. Like for example, the amount of jobs in a particular area or the amount of new jobs, it would be taken as an exogenous input. Or maybe the real estate development part we will not develop, we will take it as an exogenous input to the model, because maybe it is difficult to estimate in Indian conditions where a real estate developer, or rather the real estate developer will not share data where they are going to develop in coming years or so on. Or we may study the existing pattern of development of real estate and we can infer from that. So it could be endogenous, it could be exogenous as well. And if it is exogenous, then this is not a part of the model system. It has to be taken. So the model coordinator has to take into consideration all these things and then run these different components in sequence, so that we at the end of our simulation period we get some output, and we can keep on simulating it for a certain number of years, and then and that's why we require the data to be stored and also to be visualized as well. So this is the software architecture of our urban simulation system, and we have different variations of this in different models, land use transport interaction modeling systems that are used commonly. So now, tying up with all the theory that we learned regarding different land use transport models that are being used in different countries or in different places, and along with that, the kind of transportation modeling that is undertaken in our country, we see that mostly the comprehensive mobility plans are the ones where we need, which requires a land use transport modeling approach particularly for Indian cities. So in India, in most cases, the comprehensive mobility plan was there from 2013, 14. Many cities did their comprehensive mobility plans, but 2018 there has been a revision where there is a requirement for a very, very integrated land use transportation of the components that are part of land use as well as of transportation, which was not earlier stressed on. So now we require more components of land use in the land use transportation modeling process. Earlier in CMPs, usually the CMPs have been based on a 4-stage transportation demand model, which is primarily a transportation part of the land use transportation modeling process. So there was not much of land use modeling process. Most of it was exogenous input, and we have a 4-stage model to take this input of jobs and the existing land use that is available, and to predict the amount of trips that are generated for this particular setting of different kinds of lands or different jobs in different areas. So basically it's a doubly constrained model of land use transportation, which is nothing but a 4-stage, or it is like a gravity model, and it just determines how people move from one zone to another using what mode and along which route. So this is what CMPs have been primarily determining. And then what happens, this is usually in CMPs we determine for the business as usual scenario, and then based on whatever has been given in the master plan, like proposed land use or proposed or projected population, projected jobs, we can use those data and then develop the scenarios, or we can have also separate scenarios as well. But primarily if we go with the master plan projection, using that we can also determine the transportation requirement for that particular urban area using a 4-stage model, and that what was happening in earlier CMPs. So growth scenarios can mean that, okay, what are the, in addition to whatever has been projected in master plan, certain other growth scenarios like certain new areas where development can come up, or maybe TOD could be thought of in certain areas. This kind of things were thought of, and we can plan for higher density of development in those particular zones, and that also means that new jobs or new population will be allocated to those new TOD zones. So this is what was being done. So there was no proper modeling of how the land use is transforming. What was done was, we take inputs, exogenous inputs of how land use is going to be in the future years, and based on that, what should be the transportation requirement, or if the transportation is adequate or not. So, and the allocation process of population and jobs, and in most cases, was based on existing density, capacity and accessibility characteristics of particular zones. That means in 4-stage models, as we have discussed in the Hyderabad development plan, there have been different zones have been designated, the total area has been divided into many TIZs. Now for each zone, based on the existing density, capacity, accessibility, people could project the future population and jobs. But as you understand from the modeling process that we have learned, these are very, very basic models which were, or very, these procedures were taken up much earlier, and it has got no relationship with how in future areas are going to grow in terms of population or jobs. If we consider that the existing trend will continue, then only this thing is valid. So as we can see in existing CMPs, we neither have a real estate development model, we neither have location choice models for households and jobs, neither we have vehicle ownership and land price models. And what is done is, taking certain scenarios, we can say that, okay, this will happen, and accordingly we can predict the transportation requirements for a particular city. So if we look at the different CMPs that have been taken up, like in Mumbai, it's a standard 4-stage travel demand model using the M software. Then in Bangalore, it's again a traditional 4-stage integrated land use transportation model using the Cube software. And in Kolkata, we have a CMP, but there is no information available if a model has been done or if a software has been used. Then we take Visakhapatnam, a conventional 4-stage model is done, but the document doesn't mention what kind of software has been used, and so on. So as we see that primarily in Indian urban areas, CMPs have been basically only the transportation planning component, and it has got no planning or no modeling or no determination of the land use component that is going to happen. So the comprehensive transportation study for Hyderabad metropolitan area, we have shared the TSZs for this particular study, and here the land use, just as an example, land use growth scenarios have been estimated, and population and employment distribution has been done as per the land use growth scenarios. There have been different scenarios have been constructed. In scenario 1, it is done as per past trends. Population projection has been based on time series data, and employment projection has been based on certain logical assumptions which come along with that. And in scenario 2, the existing master plans available for that particular area has been considered, but it has been found that the master plan or development plan overestimates the population, and then certain modifications was done, but more or less it has adhered to the land use and proposed land use that has been given in the master plans, and that is the future land use for that particular urban area. So no modeling was taken up. And similarly in scenarios 3 and 5, here, even though models have not been taken up, some growth centers has been identified based on TOD principles, and based on the accessibility of that growth center, the existing land use and existing concentration of population, employment, and also capacity constraints of that particular area, weightage has been given to each area or each growth center, and then based on that weightage, population has been allocated, and then jobs have been allocated following certain assumptions and certain or following similar procedure. So this is what has been done. So formally we can see that there is no prediction of land use transformation, no prediction of location choices. So that is missing in this particular models. So just concluding, so we can say that based on the requirements of comprehensive CMPs, there is a need to introduce this land use components inside our land use transportation modeling frameworks, which is missing, and this course will actually look into development or detailing out this particular model components and how they could be integrated with the existing 4-stage modeling system that are there, and how the total overall integration could be done. That is the focus of this particular course. So looking into land use transport interaction models, we see that while land use transportation models covers the land use part and also the transport part, a big part which is environment has been left out. So considering today the problems of global warming, greenhouse gas emissions, air quality, traffic noise, gradually we are losing open spaces and green spaces. We need to modify our land use transport models into land use transport environmental models, so that the different environmental parameters or characteristics are inbuilt into the model. That means if I change a certain land use, certain environmental aspect would also be affected, and that will lead to a positive or a negative impact. So the model should be able to endogenously predict those kind of effects. So, and not only that, it needs to predict the effect on each individual or each group of individual who is being affected because of those particular changes. So this is something which needs to be incorporated in future land use transportation models. Then of course there is the macro and micro debate. So as we have discussed, we can go into micro scale, like we can go into grid from TSZs, we can further divide the area in form of grids, or we can even go to the plot level, which will actually improve accuracy of location choice models, or at the same time it also brings in a lot of challenges as well. For example, if we go for micro, then there are many problems that come along with that. For example, data availability is a big thing in this. We need to have data at that particular level, and not only that, if the models are predicting for this micro levels, there are other problems that happen. So if the number of people is less, or suppose the number of jobs is less, but the location choice is multiple, then the model's prediction would be different for different runs. So that is a problem. That means at different times the model will run, it will have different predictions. So this kind of problems will arise. So this could be avoided if it was at a more macro level, and planning for this is one. Then we can also think what we are this land use transportation models only is talking about looking into urban growth. That means it can predict how the urban area is growing, but it cannot predict, or rather it is not. It may be able to predict decline, but it is not. Because of the model structure is oriented towards predicting urban growth, there may be some unforeseen problems which may arise because of many of this decline. Many urban areas are are actually declining, so people are moving out of those particular urban areas. So planning for those areas also needs to be considered. Then if you look into the transportation part, recently the entire transportation service has changed, or rather it's going through a lot of changes. For example, e-mobility and also shared mobility. So not only shared mobility, shared services, and like for example food delivery services to households. So this kind of services are changing the way people live, they are changing the activity pattern. So that will have a big effect on future development plans or future land use transportation plans. And then effect of real-time information on traffic. So instead of looking into only peak hour mobility, we need to look at the mobility for the entire day, because real-time information actually gives a person to choose or defer his travel to a time when there is not much congestion, or he can also choose his route, because looking at real-time information. So how to incorporate this into the actual modeling process, and then of course integration of machine learning techniques at all stages of analysis. So these are this will improve accuracy and from standard multinomial or other logic models, but at the same time this requires a lot of data. So how and data in today's context, there is a lot of data available from various sources like for example Google, or from the bus transportation system in an urban area. So a lot of data is available, but we require machine learning to actually analyze this data, and how in different parts of our model we can bring in machine learning as well. So these are the different future challenges that I envisage, in which is going to be more relevant in the coming years, and this is where gradually we will see how the land use transportation modeling process will transform. So these are some of the references that you can follow. So in conclusion, we can say integrated land use transportation models consist of several related components which are tied together in form of an urban simulation system. And currently, advanced urban land use planning models for Indian cities are yet to be deployed. So we have basic models, which is primarily the transportation part. And considering current requirements and developments, there is need to further modify land use transportation models to be more sensitive to policies and their effect on environment. Thank you.